The sun just threw 1 billion tons of superheated gas at Earth. It's traveling at over 1,000,000 miles per hour. We have maybe 15 minutes warning before it hits. This isn't science fiction, it's called space weather. It happens constantly, and when a big one hits, it can shut down power grids, knock out satellites, and blind GPS. Here's what's actually coming toward us right now. A coronal mass ejection begins deep within the sun's outer atmosphere, in a region called the corona. Here, the sun's magnetic field twists and tangles under the constant churn of boiling plasma. Over hours or days, magnetic energy quietly builds up, storing power like a wound spring. When the tension becomes too great, magnetic field lines snap and reconnect in a sudden, violent process known as magnetic reconnection. This is the trigger, a release of energy so intense it hurls a vast bubble of plasma out into space. The plasma itself is not just hot gas. It's 1 billion tons of charged particles, mostly protons and electrons, locked together with magnetic fields. The eruption tears free a structure known as a flux rope, a giant twisted coil of magnetic field lines carrying plasma along for the ride. As it bursts away from the sun, the ejection forms a distinct 3-part structure. A bright core, often a piece of solar prominence, a dark hollow cavity, which is the magnetic flux rope itself, and a bright leading edge where the solar wind piles up ahead of the advancing cloud. This is not a gentle breeze. The typical CME launches with a mass of about 1.6 billion metric tons, enough material to fill a mountain valley. All of it is shot into space in a matter of minutes, powered by energy released in the blink of an eye. The real drama, however, comes from what happens next, how this immense invisible cloud races outward, carrying the sun's magnetic field across the void toward Earth. A coronal mass ejection doesn't drift through space, it races across the solar system at speed that defy everyday experience. The distance between the sun and Earth is about 93 million miles, a gap so vast that even light takes over 8 minutes to cross it. Yet a fast CME can make the journey in just 23 hours if it's moving at 1,700 kilometers per second. Some have been clocked at 1,845 kilometers per second, shrinking the trip to just 22 hours. To put that in perspective, a commercial jet travels around 900 kilometers per hour. A bullet from a rifle moves at about 1,700 miles per hour. The CME's plasma cloud leaves both in the dust, covering more ground in a single second than a jet does in a minute. As the cloud barrels outward, it expands and thins, but its speed means there's almost no time to react once it's detected. For most of its journey, the CME is invisible to human senses, no sound, no warning, just a silent countdown as it closes the distance. The entire drama, from solar eruption to near-Earth arrival, can play out in less than a day. Every hour that passes brings the plasma and its tangled magnetic fields closer to Earth's magnetic shield, compressing the timeline for any protective action. The sun's outburst becomes a ticking clock, with the final hours often slipping away before most people even realize a threat is on its way. Far from Earth, a network of solar sentinels stands guard against the sun's outbursts. The first line of defense is the LASCO coronagraph mounted on the SOHO spacecraft. Orbiting at the L1 Lagrange point, 1,000,000 miles sunward from Earth, LASCO blocks the sun's blinding disk to capture faint details of the corona. Its cameras can track a CME from just above the solar surface out to 30 times the sun's radius, watching as the plasma cloud expands and speeds away. White light images from LASCO reveal the eruption's mass, velocity, and direction, giving forecasters the crucial early data needed to estimate whether Earth is in the crosshairs. But LASCO can only see so much: the orientation of the magnetic field, The detail that determines the severity of a geomagnetic storm remains hidden until the last moment. As the CME barrels across space, the next sentinel waits, the dissects satellite, also stationed at L1. Unlike LASCO, dissects does not take pictures. Instead, its sensors measure the solar wind's density, speed, and most critically, the direction of the interplanetary magnetic field. When a CME's shock front sweeps past dissects, the instruments detect a sudden surge in plasma and a shift in magnetic orientation. This is the final warning. From the moment dissects registers the change, operators on Earth have just 15 to 60 minutes to brace for impact. That short window is all that stands between a routine day and the sudden arrival of a billion-ton plasma cloud at Earth's doorstep. Dr. Priya Patel, a solar physicist who monitors these real-time feeds, describes it as a race against the clock. LASCO shows us the threat is coming, but dissects tells us when it's about to hit. Sometimes, we have less than half an hour to activate protective measures for satellites and power grids. It's a tense, high-stakes chain of alerts, one that has become essential as our world grows more connected and more vulnerable to the sun's storms. A billion-ton cloud of plasma does not simply brush past Earth. When a coronal mass ejection reaches our planet, it slams into the magnetic shield that surrounds us, a collision that happens 60,000 miles above the surface, far beyond the reach of weather balloons or jetliners. The first sign is a sudden compression of the magnetosphere as the CME shockwave plows into the invisible boundary that usually protects us from the solar wind. This collision forms a heated sheath, a turbulent region where solar and terrestrial plasmas mix, temperatures spike, and magnetic fields twist together under enormous pressure. But the real drama hinges on a detail hidden within the CME's magnetic field: the direction of its BZ component. If the incoming field points south, opposite to Earth's north-pointing field, the two snap together like magnets with opposite poles. This merging process, called magnetic reconnection, acts as a cosmic gate. Southward BZ unlocks the door, letting energy and charged particles pour into the magnetosphere. If the field points north instead, the gate stays mostly closed, and the storm fizzles. When reconnection occurs, the effects ripple around the planet. Charged particles spiral along magnetic field lines toward the poles, colliding with atoms in the upper atmosphere and lighting up the sky with auroras. During strong events, these lights can spill far beyond the Arctic and Antarctic, painting green and red ribbons over cities that rarely see them. The aurora is only the visible tip of the iceberg. Beneath the spectacle, the sudden surge of energy stirs up electrical currents in the atmosphere and ground, setting the stage for disruptions that reach deep into the systems people rely on every day. At 2:37 a.m. on March 13, 1989, the Hydro-Quebec power grid experienced a sudden surge of geomagnetically induced current, GICS, flowing through its long transmission lines. Monitors at the Manicouagan substation recorded peaks over 100 amps, but it took only a sustained 5 to 10 amps to trip the first protective relays. Within just 92 seconds, a cascade of relay shutdowns swept across the grid, cutting off power to 6 million people. The blackout lasted 9 hours, plunging a fifth of Quebec's population into darkness. Grid director Jean-Pierre Lapierre later described the moment as a total loss of control, a system designed for everyday storms, overwhelmed by the invisible force of a solar eruption. Engineers found transformers overheated, alarms blaring, and voltage collapsing before anyone could intervene. The event revealed a hard truth. A billion-ton plasma cloud, launched from the sun days earlier, had reached Earth and sent electrical shockwaves deep into the ground, proving that space weather can disrupt modern life in a matter of minutes. Satellites in low Earth orbit face a different kind of threat when a coronal mass ejection arrives. As the upper atmosphere heats and expands, air density rises hundreds of kilometers above the ground. This invisible swell drags on satellites, slowing them down and pulling them toward Earth. In February 2022, SpaceX lost nearly 40 Starlink satellites just days after launch, swept out of orbit by a geomagnetic storm that followed a CME. Older satellites, too, have to fight harder to stay aloft, burning more fuel to maintain position. GPS signals, which depend on stable layers of the ionosphere, can suddenly wobble, throwing off navigation by several meters. During strong storms, pilots flying polar routes may lose radio contact and have to reroute, adding hours to flights. But the story doesn't end with disruption. Satellite operators now receive alerts from agencies like NOAA and ESA, sometimes with less than an hour's notice. They can switch spacecraft into safe mode, rotate solar panels to minimize charging, or even boost orbits in anticipation of increased drag. Power grid managers reduce load on vulnerable lines, and airlines plan alternate routes. These steps don't eliminate risk, but they buy precious time, turning a billion-ton plasma cloud from a sudden disaster into a challenge that can be managed. The sun's storms are relentless, but so is human ingenuity. Right now, billion-ton plasma clouds cross 93 million miles toward Earth, disrupting systems we depend on but rarely see: GPS, power grids, satellites. Space weather isn't science fiction. It's real, unpredictable, and growing harder to ignore. Our technology is only as resilient as our awareness. Thanks for watching.